The topic for today is real-time data processing for the people. In other words, how far it is to nirvana. And the motivation for today is the very big disparity between the tools which are available for developers, for professional developers, and for non-professional developers, in case you want to act on real-time data. And the situation is that there are many use cases where domain experts want to build algorithms which act on real-time data, and simply they do not have the tools, appropriate tools, which would allow them to do so. And they have to delegate this work to professional developers. And again, there are many use cases where this situation is far from optimal. So we'll be talking about the features required in tools, development tools, which address the non-professional developers market, right? Let's narrow down what kind of real-time applications we'll be talking about, because this talk is not about any real-time application. It's about specific subset of real-time applications, and the subset which can be defined or synthesized as decision-taking systems. So these systems follow quite a common pattern. They take an input from the data stream. The data stream contains events, or I just get a request with some kind of an inquiry, and they process this data to deliver the decision and put the decision into the outgoing data stream, or just deliver this decision in the response if the origination came from the request. The use cases would be fraud detection, next best offer, dynamic pricing. Also, there are many use cases which are purely from the streaming domain. So analysis of sensor readouts or clickstream analysis. Real-time marketing use cases also work very often on streaming data. Industrial IoT preventive maintenance. And last but not least, telco and computer network events analysis for whatever, right? For performance, for fraud, for marketing, etc. The third group of use cases are about complex deployment of ML models. Cases like credit scoring, fraud detection, again, next best offer, etc. And by complex, I mean situations when not all the data required at the input of ML model are immediately available when the decision algorithm is called. So these are the situations when there has to be some pre-processing before ML models can be called. Maybe there has to be lookup to feature store to bring up the features required by the ML model. Similarly, after all the ML models are run, there has to be some post-processing and business logic, and only then the final decision is delivered. And if you look at the tools available to non-professional developers, I would say that the situation is pretty grim, and maybe it's also pretty grim when it comes to professional developers, right? Because not everybody has PhD in Flink, Kafka, Pulsar, and Spark. And maybe people would prefer some other frameworks which would make their life easier, right? I have a couple quotes here, so I will just let you read them. I'll not be reading them. Chip Huyen is a very important person in ML processing. I'm sorry, I don't know how to pronounce this name. Ying Jun is a founder of Rising Wave. Rising Wave is a streaming database. Here we also have an example of a pretty well-established ML deployment tool, Seldon, how deployment of complex ML model is defined. Basically, you have to define a YAML file. Okay, by the way, you see this is the situation when two models are run in parallel, and then there is some kind of a combiner, whatever it is, which combines the outputs from these two models to produce the final decision. In order to model something like this in Seldon, you need to create this custom resource definition in Kubernetes. It's in the YAML. Well, I'm a computer man, so I understand what's going on here, and I know what it is about. But if I were a domain expert, a person who wants to build a specialized algorithm for whatever, I wouldn't dare doing this. So I would never, as a domain expert, I would never like to use to create such a specification. And finally, we should look for a second on streaming SQL, because this seems these days to be a language of choice for many to analyze streaming data. And I would argue that while it's a natural entry path for many, especially if people come from SQL background or heavy data analysis background, it's an impediment. It blocks many people from entering streaming actions on real-time data, just for the reasons which I have here on the right-hand side. First, SQL is non-stitchable, right? The other word I could use is non-composable. If you want to stitch or several SQL statements together, the question is, how do you do it, right? You have to have intermediate tables where you put the results from one query and then a subsequent query reads from. If you are in the streaming situation, you have to put this data into Kafka stream. The Kafka stream has to exist before, so you may end up with lot of Kafka streams. Well, operationally, it can become dangerous because you may have a lot of topics to manage or a lot of tables with potentially millions records. Well, this is far from ideal. So what people do is that they do not they don't compose their logic from smaller pieces. They just create one big, sometimes monstrous SQL. And of course, in such cases, such streaming SQL can be very difficult to understand. We have a prospect who approached us with a case, and they have an SQL which has 8,000 lines of code. 8,000 lines of code. I think it's completely unmaintainable and probably impossible to understand. So I would argue that what we need is some kind of stitchability or composability, right? We want to build our logic from small blocks, bricks, something that you can stitch together like you stitch Lego bricks, or something which would work like a chain, like chaining in languages like Java or Python, right? You use this dot to chain functions one after another. Third reason why SQL is not perfect is that these data, JSON is lingua franca for data. And clearly, SQL was not created for this. Of course, there are extensions which allow us querying JSON data as well. But if the data structures are complex, I would say it's far from optimal. And finally, okay, SQL will work for streaming, but what about simple request response? Why would I use some other tool, a non-SQL oriented SQL tool, if my real-time case is simply request response, right? I am called and I have to deliver a decision. Yes, this is fraud. No, this is not fraud. Or yes, give this customer a loan or not. So my bottom line is that the situation is pretty grim. The tools which are on the market and the languages which are used, like the streaming SQL, is more of a blocker rather than like a path to the future. And it's a good moment here to pause for a second and reflect on the past developments, because almost 50 years ago, two very important applications which made the history in computing hit the market. These applications allowed people to analyze data at rest, right? Data at rest in opposition to data in motion, about which we are talking today. And these tools, or this category of applications, caused a revolution in computing. Okay, I would say what I mean. I'm talking about Lotus 123 and VisiCalc. They hit the market around early 80s. And for quite a while, people were buying PCs or PC clones just to run spreadsheets. Spreadsheets were so important, and they were so important and successful because they proved that people can crunch static data without having PhD in programming. Today, these days, hundreds of millions of people create spreadsheets, and they even don't think whether they code, or is it citizen development, is it low code, whatever. They just create spreadsheets and crunch data. Of course, some of those spreadsheets are very simple and trivial, but some of those spreadsheets are pretty complex. And the main argument here is that you do not need heavy computing skills, heavy IT development background in order to analyze data at rest. So I would argue that there are a couple lessons to be drawn from this story. And for me, there are three main ones. The first is compelling user interface metaphor, right? If you think about spreadsheets, it's not about clicking or drag and drop. The metaphor, the excellent metaphor, is this spreadsheet itself, and cells as something which is so intuitive. This data in columnar and row format, it just so compelling, right? So the success is not in okay. The second point is that spreadsheets prove that some form of coding is okay. It's not fully fledged coding. It's not procedural coding. The languages which are used by spreadsheets are called expression languages. So it's a subset. They are much simpler than, say, Python or Java, but they are very natural to use. They kind of follow the intuitions which we have from school. Everybody who did some mid-grade level school maths in school understand what's going on there, right? And the third point is about the immediate feedback, right? You probably remember your first encounter with the spreadsheet when you entered your first formula into the cell. This was probably like 2 + 2 equal 2 + 2. You hit enter and you've got immediate answer, right? And I remember this experience until today, and I remember this wow moment. And if I entered something wrong, that the spreadsheets immediately yelled at me that I made mistakes. Something is wrong here, right? So it's very far from the seldon.yaml file, which if you happened to compose a correctly formatted YAML file, but with wrong contents, you'll probably learn it only after the deployment, so pretty late. So these are the three main lessons I believe we should draw from the success of those tools, which happened 50 years ago, right? And it's amazing that after 50 years, we kind of are like, in the early 80s with our real-time data. So we have our unhappy domain experts who would so much like to create and polish their decision algorithms, but they have to delegate this work to people who have PhD in programming, right? What are the domain expert needs? They want to own the changes. I would argue they want to build these algorithms. They want to polish them. They want to iterate on them. They want to improve these algorithms, because some of those algorithms are like a moving target if you are in the fraud space, for example. They want very short iterations. Because if you have to experiment, you don't want to wait for 1 week for your team of programmers to apply a change and then stage it to whatever next environment. No. You want to experiment yourself, right? Real-time algorithms, to a large degree, are about experimentation. And finally, you want to do it without a need for PhD in Kafka, Spark, Flink, Docker, whatever, right? You want to deal with data only, right? As exactly as it is in the case of spreadsheets. So, let's think what could be the path forward, right, from this trap, from this situation in which we are today. Let's ideate what would be the features of the ideal actions on real-time data tool. The first, even if it sounds naive, I would say it has to be innovative, right? Innovative in the sense that it has to be somehow different from what we've seen on the market up to now, right? Because clearly these attempts were not so successful, right? So something must be missing. By the way, my argument is that the choosing SQL as the language is one of the mistakes or showstoppers for those tools. So we need some innovation, right? We will have to invent innovation here in this presentation. Secondly, yes, low code. They should be low code because we don't want to force people to learn Java, Flink, etc. But also we want them without limitations of low code, right? Many of us, if we think about low code, we immediately have another word in our mind, and the word, unfortunately, is toy. Right, so we are afraid that we'll deal with some kind of a toy which will not outlast or outlive or survive the confrontation with millions of events per second or complex data structures, etc. Right. Thirdly, we probably want the tool which addresses the full life cycle, so not just development, but also test, deploy, and monitoring. And the reason for this is that the algorithm, authoring of the algorithm is not the end of the work itself, right? If we need to function in the real-time domain, there are many layers to be added on monitoring, but also testing is not so easy, probably these are problems or aspects which were solved up to now by many people, and there shouldn't be a reason to reinvent the wheel, right? To build it again, right? Unless we are the LinkedIn with their billions of events per second, or maybe Netflix, the same. We probably can use some of this opinionated architecture for those things like monitoring, deployment, etc. Ideally, right, we would like a tool which is okay for different architecture styles. So streaming and request response. Again, SQL is okay for streaming, but I just wonder how to use it in request response case. Okay, so let's reinvent this real-time decision on data tool, right? Well, how it might look like. Okay. The first observation that comes to my mind, and this is back to the stitchability or composability, is that if you think about the algorithms in real-time domain, there are just few operators needed, right? There is a ingest the data from the data stream or from the request, which invoke the algorithm. Probably some filtering, probably some aggregating time windows if you are in streaming. Again, some filtering. Okay, there for sure there will be an enrichment needed to enrich our event or data record with data from external enrichment systems. Probably there will be some ML models run, some post-processing, writing to a sink. That's it. Just truly few bricks. Few bricks is enough. We just need the ability to stitch them together. So Our decision-taking system would look something like this, right? It would have these operators. It has to be able to look up data from enrichment serving system, and right. This is how it could look like, right? And I would argue that the metaphor used here for the UI is innovative, or maybe not innovative. Anyway, this is the graph of the algorithm, of the decision algorithm. In probably there's no other more intuitive way to depict the algorithm, right? The graph. We were told to draw algorithms in such a way from our elementary school. And yes, so yes, this is the graph, and here we have our bricks, and we want these bricks to be composable. By the way, I would also like that these bricks can work not just on sets, but quite conversely, that they can act on single events, just going back to this request response architecture style. What is next? The next, well, drawing from the experience or the success of spreadsheets, yes, we need some code. We need some code for two reasons. We need code to express data transformations, and we need code to encode our, well, Boolean conditions for flow control logic. And again, expression languages, so the language from the same set of family, from the same family of languages like spreadsheets use, would be handy here. So anything which is an expression language would be fit for the task. Ideally, we would like such a tool, such a language to have, well, for perfect fit, we would like such a language to support processing of complex JSON objects, and somehow in a very easy way allow us to use enrichments, right? Whatever the way this would be. It somehow has to be seamless. And if you think about it, DB lookups, calling REST API calls, or even ML models, it's about calling a function. So it's somehow similar to what we have in spreadsheets. So probably this could be done in a pretty seamless way. Okay, next one, as I said, because these are not toys, and real-time systems are not like toys. So we probably want a full development cycle support. We want this tool to behave to a degree like integrated development environment known by professional programmers. So we want code validations, hints, testing, and debugging support, right? We want the tool, right? Not a notepad to specify a YAML file. I'm back again to this Seldon case. What else do we want? Next slide, right? And of course, the tool has to address weak points of low-code tools. Again, to many of us, when we think low-code, we think toy. We don't trust that such a tool could deliver very high performance, very high resilience, etc. So, or allow us to create complex decision algorithms. So yes, what would be, so okay, so how could this be addressed? The first typical limitation of low-code tools is limited expressiveness. So as I shown a couple of seconds ago, this can be overcome by using an expression language, because expression language will allow us to not only to perform any transformation or to express any Boolean condition for flow control, but will also allow us to call enrichers in a seamless way. Secondly, because these tools are very often, low-code tools are very often operationally disappointing, we want that our tool is built on some kind of a fundament of rock, right? Ideally, that beneath it, it uses tools like Flink or Spark, so that to avoid a situation when the tool tries to invent something new. It's not easy to invent something new, and for sure it's not easy to invent yet another Spark or Flink. And thirdly, probably we might be worried or concerned that whatever the tool we are dealing with, we can hit the wall at some point, and there may be some functionality missing. So ideally, this should be an open source tool, just to give us more freedom on how we source changes, additions, extensions, etc. Right? Well, open source is ideal, but probably whatever type of extendability would be okay. Yes. So this was my set of features of the ideal tool from the real-time domain. And yeah, we have quite a lot of time for questions or suggestions. And first of all, I'd like to ask you what features would make you happy, right? Because I came up with my set of features, and this set was built based on our experience from building algorithms for companies who have to act on real-time data. I should be quite open about it. We have a tool which does it for us. But okay, the question is, what features would make you happy, right? What will you believe is essential for such tools?